Hello, colleagues. I'm Sergey Nikolaev. I'll be talking about adaptive management of the industrial assets as we combine. A few words about me. I'm in the lab of Skoltech Institute for Technology, and I'm in the startup of CYBERPHYSICS startup. We specialize in tackling industrial tasks. Machine learning is applied for production processes optimization. We operate with Bosch, Fiat Chrysler Automotive. These are our flagship projects. And there are plenty of Russian oil and gas producing companies, those who specialize in extraction of fossil fuels. I'll be speaking about trends, because there are plenty of trends here in this topic. I'm going to speak about the digital double, which is a hype term, but I should say a few words about it because that's what we tackle. I'll be speaking about machine learning in that respect and how we combine them with machine learning, and I'll be speaking about how we see this industry. I'll be speaking about the platform that we are developing to tackle these tasks. As for trends, it's just one of the pictures actually showing that if we take just 1% grown up effectively by the use of these ML, IoT, AI, it will generate this much money as shown on the slide. $30 billion in aerospace, for instance, and it's just a small chunk of this potential, and potential is far bigger. I hope we'll be growing in the post-COVID environment, not quite yet, but hopefully in the future it will become post-COVID. I'm showing you these plots before the pandemic kicked in and during the course of the pandemic. Worst-case scenario, optimistic scenario, even with the pessimistic scenario, as I put it here, there is an explosive growth shown at this bar chart, so obviously it will be in good demand. Digital double. So I would like to say that here is the most commonly overused term these days. It's a kind of a hyped word combination. When you tend to talk with engineers in the companies, you face with very, very negative feedback, because all people imagine when saying a digital double is just something vague and blue and nice looking, just on a slide, and that's where that's how engineers imagine it, and they don't really understand these days whether it's a real thing or it's just a hype term. We believe that it's not a hype term. Of course, it's a real technology. A simplest example, let's just take it. This is the simplest example of digital double. So we just take a simple shell, and this screenshot is taken from the video when this pendulum starts moving and the digital double starts moving. So digital double is a physical mathematical model which operates in the real-time mode, and it reflects the internal processes of the actual device, and it's connected to the physical counterpart. What's important here is that this particular digital double is the model that would analyze the processes that can't actually be measured, like, for example, tension. That's the whole essence of this digital double. But in the real environment, it turns out much more complex, because these are not just used for simple pendulum, but for gas turbine, power generating units, etc. Just take a look at the slide. This is what it looks like for a hydropower plant. You can see how this data acquisition and things are happening, and this rotor dynamic operates and the generator operates, and it's all put together in a huge model which is measuring in real time the remaining resource of the equipment, and it predicts its maintenance points and overhaul dates. But that's not the main thing. The actual thing is that this whole set of data works in unison with the real hydropower plant. That's the whole point, and only when it occurs we can entitle this the digital double. So this is what it's used in, hold on a second, yes, it's used in Switzerland. I just checked it out, it's in Switzerland. So why are we talking about this right now? Just a few years back we started having this big talk. The answer is simple, because the computing capacities and sensors have only just reached this level that they're capable of pulling it off at a big scale. Previously, it was just only possible for a smaller size object. ML. Just a couple of words about machine learning. This is as heavily overused term as the previous one. Machine learning is all about everything and nothing. It's about neural networks, about deep learning. It's not just them. That's what we need to understand. Machine learning is omnipresent. I'm not going to talk about it right now because, there have been plenty of talks dedicated to this particular topic in this conference, but it's just the time when it starts penetrating into industries and it starts helping to fix a few tasks. How can machine learning help production optimization along with the creation of digital doubles? That's the project that we carried out. It's a specific process like the molding, pressure molding in a Fiat production facility. There are plenty of iterations involved in this molding production. How to use machine learning to make sure this production process will be cut down to just one day instead of a few months. It's simple. It's visualized here. This system should be self-learning and accumulating the experience which has been accumulated in the production facility. That's where machine learning becomes useful, which can memorize quite a lot of not so obvious parameters, memorize them in detail. Let's just launch my first demo. It's a video explaining how this first product of ours works. You just log in, you launch this web page, a simple web page, you select a part, upload this part, like for example a dashboard, an automobile's dashboard. This dashboard is brand new, the system hasn't been given any information about this. So where do we place injectors for molding processes? So the system is calculating where to and predicts the output quality, and it would just take seconds here, but in normal life it would just take hours and days. Here this machine may memorize very, very complex and complicated and convoluted dependencies that had already been achieved by that production facility. That was just an example with the dashboard production. That's how this molding process looks in static. In actual fact, the system predicts the quality, the output of this production process is forecasted. Those of you who specialize in that, you can read this slide and they know how which technology of boosting we use here. Gradient boosting and ML model is used here, which has been brushed up and fine-tuned for this particular task. So in combination with this heavy-loaded machine learning, this process really helps us resolve practical tasks. So we move on, and I know that there is a statement that data is a kind of a new crude oil. Not really so, as we think, because we think data is a new form of energy. Let me explain why. Because data, unlike crude oil, is not a fossil fuel. It's not fossil fuel. It's not fossil essence, I would put it this way, if you like. It's not fossil fuel, like I said previously, and computing machines. They are not just consuming data, but also create data, and they generate a new type of energy. I put it just philosophically. Why am I talking about this? Because those companies who can generate data, generate information, can withstand these harsh realities, and there are more of them springing up. And there are two types of models, if we just simplify it. There are data-based models that use machine learning, and they can analyze data, and these models use data. They have just grown from statistics model. There are plenty of capabilities here. When you want to achieve high data automation level, you use that approach, but the physical mathematical models, or simply mathematical models of physical processes, in other words, help us create this. When we predict a failure, we can run a simulation to come up with a prediction model. We used exactly that approach. We combined this conventional approach of creating physical mathematical models, and we added the analysis, so we had it both ways. This slide depicts all of the mathematics. I'm not going to stop at it for a long time. There is a direct task that we need to resolve, and the reverse task. So this predictive and prescriptive analytics, and there are two tasks to be tackled simultaneously. A few words about how we are going to focus on the resolution of this task, and how we create solutions for managing production assets. We think that the system should look this way. You have sensors, and you stream data from those systems. It's the computer-aided design flow. You work with the platform, and each process, each item, has two sources of information. The first one being physical mathematical model, which I mentioned, and it's shown here on the top. On the other hand, there is a real flow of data from various sensors, and there are three tasks to be taken into account: online and prescriptive malfunctions analysis, modes optimization, and what-if analysis for equipment unit. For example, what happens if we replace this pump for that pump? How it's going to affect the outcomes? Certainly, this is not just hanging in the thin air. This is embedded somewhere in this decision-making process, the PBI system, BI system, and it can generate recommendations. We think a similar system, which is case-based as well, should be resolved in just a few tasks. For example, prescriptive analytics, like I said, predicting failures and explaining the reasons for such failures to occur, and very popular AR and VR simulators. And you have to provide seamless integration with AR, VR simulators, as well as optimization of the processes in real time. So you have to constantly adapt this system to what is happening. So this core of the system is the same for all of these three instances. We think that one of the important components of such state-of-the-art systems that we develop would be the common marketplace. Like in App Store, you can create your own app, and here you can upload your digital double with your own model, with some specific equipment involved, and then you can sell it. Really, that's where we are moving towards, we think. Another interesting feature, the so-called AutoML. This is where you're not just going through machine learning algorithms, you just give it to the machine to decide. It's going to optimize the actual architecture and the parameters of machine learning. It's not always necessary to use very convoluted neural networks. Sometimes it's best to stick to simple algorithms, and it's best that it's the impartial judge, the algorithm, that would decide and select the most appropriate algorithm. Once you've applied all those principles, once you've done the AutoML, machine learning, digital double, you can actually resolve the problem even with a very complicated production situation. You can use this data, put it into AutoML, and once it gives you the final result, you put it in production. You give it to those people who actually monitor the production system operations, and it will be showing how the system behaves right now and how it's going to behave in the future, and what needs to be done to make sure that it acts well and behaves well. Let's just take a look at my second demo. This is the demo of our solution entitled CYBERPHYSICS. This is what the platform I've been talking about looks like. You have projects, you can upload them there, and the principal idea here is that the solutions are uploaded from the components library. You just see what is happening on the slide. And they are connected, like they should be connected in the physical environment only. That's crucial. Then you work with database list. You select relevant sensors, and then it explains why it's a digital double system, because each physical model is having its own virtual double. Each physical sensor has a virtual sensor, so they all aligned together. So all of the models may have faults and errors, because different systems working in different areas degrade differently. So you have to adjust these parameters to suit the requirements of that particular pump or transformer. At the most interesting part, it was machine learning mode, when you adjust all the possible combinations of normal and abnormal modes, and you launch it to generate a huge data set with hundreds of thousands of combinations. And data is the new source of energy, like I was saying. You can learn to generate the data. Then the system will start identifying which problems relate to which causes is. What is the cause? What's the effect? Anyway, I've explained that. I tried at least, so if you're interested, you can just recall that video. This is what it looks like in static. Just check out the slide. This is what it looks like with the libraries on the left. That's how we implement this approach, and I will try and run the third video with the different configuration. It may look similar, but it's a different stage. It's a different operation stage. An operator will check these charts, will check these graphs. You need them for deep analysis, of course, but the system itself is analyzing them constantly. If something goes wrong, if something goes wrong with the alignment of the physical and virtual double, the system prompts you with alarm messages. Have you seen the alarm message? Exactly. For example, there's a low temperature in the combustion chamber. You have to react accordingly. Moving on with the next slide. And actually, I'm ending this presentation. I'm getting close to the end of this presentation. Of course, these systems need to be well packed, and with edge computing, with tensor processes. They are state-of-the-art solutions. I've shown you how it's done with that at the previous slide. And now a few words in conclusion. What I would like to say is that, first of all, we see some kind of a trend of vertical and horizontal alignment for the coordination of decision-making from top to bottom, then self-learning asset model, and last but not the least, speaking on behalf of the institution I represent, we need to address trainings and learning of all of the engineers and managers. They need to be exposed to all this information. It's not magic. It's all about physics. It's all about mathematics. None of the contemporary systems work without using that. So we would like to make sure that everyone learns more about that, because it really helps the business. I'm done. Thank you very much.